So we uploaded your grades on Friday, and I just handed them back to you. A few things. Number one is I have not completed going through and looking at the tests. So that means that I have done no adjustment yet to the grades right now. So what you see is the raw score. The test, the back page of the test is the score sheet. And the way to read that is it has something like this. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, like that. It has something like that written, where I just made up the letters, obviously. The way to read that is anything that has a dash is correct. This up here is the key. Those are the correct answers. So if it has a dash, that means that you entered or wrote the correct answer. If it has a letter, then that means it was incorrect. You answered the letter that's shown rather than the letter that is above, rather than the correct one. So that's the way to read that. It was pointed out to me just a moment ago. Remember, there was one question that had two answers that were identical. And when I was setting up the key, I forgot to set it to make both of those answers correct. So I need to go back. Which number was it, Rachel?
20.
Number 20? So I need to go back and fix that. So for some of you, your grade should go up there because obviously if you answered the right one, you answered the right one. So that's how to read things. I'll go back and fix that. If you find anything else that looks to be an error, please let me know. Right, we want these to be accurate. And I still haven't decided how I'm going to actually make the grades, but your grade will certainly go up from what is shown now, not the other way around. Any questions about that?
So are we just gonna go over the test right now? Or
Actually, no, we're moving forward because I haven't actually gone over the test myself yet. Other questions? Then, continuing on with geology. Now, a lot of the things in the slides today I've already talked about. So here I'm going to basically look at some pictures and point out some details and go through a lot of slides rather rapidly. So we've already talked about sedimentary rock and the process of sedimentation. This one here, though, talking about how coal is made, is I think one that's good for students to have knowledge of. You're going to be like a grade school teacher. That's what I pretty much assume for my students here. I know Sam being the exception about that's not his goal. This is something that you think about a lot, like where does oil come from? Where does coal come from? And so the process where these come from is you start with, and this is specific to coal. It's going to be a little different if you talk about where does oil come from. There's a lot the same, but there's a little different. So you start by having organic material. Notice we have plants here in a swamp. And those plants then get buried. So you have, if you will, fossils of plants. Fossils can be fossils of plants or animals. But the plant material then gets squashed and compressed. And under the pressure and heat, the chemicals undergo reactions to create you see the terms here go from peat to lignite to bituminous to anthracite. But this here is, these are coal things that are pulled out of the ground for people to burn. So if you have coal, if you're burning coal, what kind of material was it originally? What was it originally? Okay, for coal, it was plants. Yeah, so if you're burning coal, you're burning plants. Now, oil usually is coming from animals. So for oil, you're going to have animals that died, were buried, compressed with heat. And once again, you had the chemical reactions that occurred because of the pressure and heat that resulted in them decaying and producing the oil. Now, if you think about that, we have huge oil deposits. What does that tell you about the animals that died?
There was a bunch.
Yeah, there must have been a bunch of them, like a really large bunch of them, very large number. And so, once again, people who believe in creation often will say that, or creation, who believe in the biblical flood, will say that during the flood you had mass deaths of animals, and that's likely what caused all of this oil to be produced. That was the beginning stage. Now, if you don't believe in a flood, that doesn't mean, you have no answer for where the oil comes from. In fact, if we go through geology, we have what we call mass extinctions, events where lots and lots of animals die. One of those mass extinctions, for instance, is the KT boundary, the boundary between the Cretaceous and the Tertiary. I should remember this.
Cretaceous, Tertiary.
Yeah. Where you have something like 97% of all animals died. And so you have lots and lots of deaths, a mass extinction, and so you should expect to have had, lots of animals then that could have been compressed and producing oil in the future. And that 97% is just coming from my memory. It could be 80, I don't know. But there are a few events that are just mass extinctions where far more than 50% of all animal species disappear from the fossil record. Okay, metamorphic rocks are rocks that have been heated and put under pressure to change. So we talked about the three types. We had igneous rock, sedimentary rock, and metamorphic. So metamorphic rocks can be made from any of the three types. From igneous rocks, typical igneous rocks would be something like granite or basalt. Or from sedimentary rocks, things like sandstone or slate or shale, or even other metamorphic rocks. Metamorphic rocks can be metamorphized again. And when metamorphism occurs, you can have some recrystallization and you can have the mechanical deformation, that is the changing. So here is an example of how metamorphism could occur. So you have here a granitic pluton. That pluton is it's magma that is solidifying, cooling, forming a solid rock very slowly. And on the boundaries of that pluton, you go from hot enough to melt rock to not hot enough to melt rock. Well, in the region from hot enough to not hot enough, you have an intermediate zone where it partially melts it. And that's where you would have metamorphism. And this is showing another example of a hot spot, and then on the borders, you'd have metamorphism occurring. Let's just keep on going here. Here's some types of metamorphic rocks. So this is slate. This is what you would use typically for a blackboard. I say typically, it makes really good blackboards. You can make cheesy blackboards out of other things, like painting something, but the slate makes really good. This here is schist and gneiss, hence leading to many jokes about classifying rocks and some inappropriate mispronunciation there. You see here the gneiss, you can see clear signs that it's been deformed, right? You would have to assume that was at one time a straight line and it's been pushed and deformed, giving it that funny shape. And marble, of course, has the same types of things in it, clear signs of the metamorphism. When you talk about the metamorphized rock, you have non-layered or layered, non-foliated or foliated. And so marble and quartzite are things that are not layers. You can't peel them. Whereas, I think slate is layered. And for the rock cycle, we'll end here with, this here is a cycle of how rocks are made. I always start at the top here with molten rock. Because whenever you melt rock, you know you're going to start with one type of rock. Molten rock is going to freeze and form igneous rock. Igneous meaning fire formed, because it was melted. And then you're going to have weathering, transportation, and deposition. You're going to have something that breaks the rock apart. It could be chemical weathering, such as if it's limestone, water would erode it away just because it dissolves in water slowly, dissolves in acid faster. Or it could be something like an action of water, the freeze-thaw cycles of water getting into cracks and breaking them open. Or it could be people walking off of the pathway and breaking stuff up. Then transportation. On Earth, that transportation is often going to be either water-induced or air-induced. Right? Air will blow stuff, water will transport stuff. But it can also be done by wildlife. Animals can transport, humans can transport as well. And then you have deposition where the transportation stops and it starts building up. And so in those places where it builds up, oftentimes that's going to be where water goes from fast to slow. Fast water will carry a lot of sediment. When it slows down, it can't carry as much and it drops it out. And so you have things like deltas. You have the Nile Delta, or what is it called down there? Like in New Orleans, there's a delta. Anybody remember? But deltas are places where you have a stream carrying a lot of sediment, comes into a body of still water, and so that sediment comes out here and fills up a region, something like that. And since delta looks like this, they call it a delta. And so that delta is produced by the sediment being laid down because the speed of transport slowed down. It drops sediment out of the fluid, making the layers of sediment, which over time, with pressure and chemical change, can become cemented into a single rock. And then you have sedimentary rock. Now you could have igneous rock go straight here, or you can have the sedimentary rock go here to metamorphism. You could also have sedimentary rock could go to here, be weathered, and transported again. So the cycle does not have to be a circle. It's not the circle of life. It is different options that can occur. So any type of rock can be metamorphized. Any type of rock can be weathered, eroded, transported, and deposited. But that is our circle of rocks, of rock formation. Now, I've talked about seismic waves. I did a lot of talking about seismic waves in lab. So let's just get to pictures. Already talked too much about that. The types of waves. I said there's the primary wave or P wave. It can be called primary or pressure wave. The P could stand for either one. And the pressure wave is a longitudinal wave, like a sound wave. If you look in that picture, it's kind of hard to tell, but it has vertical lines that are closer over here and farther apart there. That's indicating that you have a motion that is making wider and narrower separations between what was initially all the same separation. Then we have the S wave. It says here secondary, but it can also be named the shear wave. Right? P could stand for pressure or primary. S could stand for shear or secondary. The primary and secondary tells you faster and slower. The P wave is faster, the S wave is slower. The pressure and shear tells you if it's longitudinal or transverse. You see in that secondary wave, it's very clear that the motion of the ground is up and down, whereas the wave in all of these pictures, the velocity of the wave is traveling that direction. So here you had the displacement was the same direction as the speed. Here you have the displacement is perpendicular. That's the difference in transverse versus longitudinal. These bottom two, the Love waves and Rayleigh waves, are exclusively surface waves. The first two, the S wave and the P wave, those can travel through the bulk of a material. But Love waves and Rayleigh waves are surface waves where you are combining both an S wave and a P wave together.
What do you mean through the bulk of what material?
In this case, the Earth. So traveling through the bulk of the Earth, not along the surface, but through the middle. So the Love waves and Rayleigh waves are only surface waves. Transverse and longitudinal can go through anything. And I'm not going to go to the video. This here is kind of interesting. I like to look at the dates. In 1906, some dude, we'll just call him Richard. He's got the name Oldham there. He observed that the waves travel together for a distance and then encounter a boundary where the S waves stop and the P waves refract. How would he know that? He wasn't in the Earth to see it. How could he make such a discovery if he's not in the Earth to see? Hey, the S waves here are stopping, and the P waves are refracting, which means they're bending, changing direction, by continuing to travel. How do we know anything about what's going on inside the Earth? How do we know anything that's going on inside? When my arm is broken, we do X-rays. Well, for the Earth, we do wave analysis like an X-ray, but instead we're using these seismic waves. So he's looking at the waves that are coming through the Earth. And essentially what you have, I don't think I have, oh, I do. Here's a picture of it. So what you have is in this region from here to here, okay, so the earthquake occurs there at the epicenter. You have both S and P waves getting to the surface. But then there's this region that's called the P wave shadow zone. No P waves. That's what he observed. So you have a region where there's no P waves. Well, P waves are going to be refracted. And so that region where there's no P waves is where you had the P waves were refracted at different angles, so it indicated a barrier. But then there's something more important. If you look down the lower picture, not only is that a P wave shadow zone, it's also no S waves. There's no S waves going from here all the way to there. So at that layer, the P waves were being refracted or bent in a different direction, as indicated by the change in direction shown right there. Right, it was coming like this, and also it bends like that. But the S waves just stopped. No S waves went through. S waves have to have a solid to go through it. They can't go through a liquid. And so the absence of S waves says there must be a liquid region in the Earth. So that's how we come to understand there's a liquid region, because of the S waves having this big shadow region. And because of this P wave shadow zone, we can make some determinations about the speed change when the P waves go from the mantle, the solid part, into the liquid core. Now it gets more interesting because you have some really funny things that occur. It's not actually shown here very carefully, but when the waves get to here, they'll go around this board boundary and send off secondary waves. And those secondary waves are observable, so they can see waves that indicate there's a boundary inside of the liquid with something solid. So looking at the waves that come out, they can infer there's a solid core inside the liquid core. Now, obvious questions you may or may not be thinking about is, how is it possible to have a liquid in the center? We can have a liquid in the center because the high pressure and the high temperature melts things. But then how do you have a solid inside the liquid? Well, if you really, really compress things, it pushes them back into solid form. And so even though it's super hot in the center, it's so high pressure because of the weight of everything above it that it makes it back into a solid form. So this, what I've just discussed, is the taken together, all of their work. We have the crust, the mantle, the core, and the core has the liquid and the solid regions. The core is composed predominantly of metallic iron. How do we know that? Once again, no one's ever been there to sample it.
Is it because the heat waves they go through it?
Well, we can determine the speed, which helps us to identify something about the material. But the actual reason we, quote, know this, end quote, is really more basic. Iron is the densest common element. If it's the densest common element, that means that it's the common element that will have sunk the most. So when you get to the center, you're going to have the one that sunk the most, the densest one. And so that's really kind of an assumption based on, okay, so the Earth is 1/3 iron, and iron is more dense than the silicon or the oxygen compounds. And so the iron should sink, so we should have most of the core being iron. So it's a deduction. It's not a direct measurement. None of these things are direct measurements. They're measurements of what we can see at the surface and infer. Just like when you have an x-ray done of your arm, it's not a direct measurement. Nobody saw the bone, but they saw the waves that came through, and they could infer what was in there from the waves that came through and the ones that did not. I can't remember if I put this on the homework or not. Here is, instead of showing it as a spherical wedge, showing it as a rectangular chunk so it's easier to get your eyes on. The inner core, that's solid. The outer core, that's liquid. Then you have the lower mantle, the upper mantle, the asthenosphere. You see it says plastic. That does not mean it's a plastic like you put in the microwave oven, or you should not, because you don't want to get, I don't remember what the BPAs, I don't know. Plastic means that it can deform, that it'll ooze a little. And then you have the lithosphere up here, that is the rigid rocks that float to make the tectonic plates. And there's the Mohorovičić discontinuity shown the bottom of the crust. Let's see what else I want to talk about here. Once again, I don't remember if I have too much about this. Why do we have the crust here much thicker when it's a continental crust than when it's an ocean crust?
Does that have to do with the plates that you talked about before?
Those are making parts of the plates, but it doesn't have to do with the plates. Because of what they're made up with. The continental crust is low density. Because it's low density, you're going to have equilibrium. That is, you're going to have the same net force pushing down in all directions, or it's going to bulge up. And so here, where you have a low density material, you're going to have more material piled on to get the same weight. And so the continental crust is much thicker because it's lower density. And so it has this root, it goes down lower because just like an iceberg, to support the stuff here that's above the level of the normal surface, you have to have a much bigger amount that's down below. So that's why it's so thick, because you need to have basically the same weight. You know, if I take a line here and I break it into boxes, the weight in each of these boxes needs to be the same. And if I have less dense material, then it's going to have a taller box to get the same weight in it. Whereas you have higher density for the ocean floor, the basalt, and thus it's not nearly as thick to get the same weight. So isostasy is the name for that being in equilibrium. Iso means equal and stasis means standing. Equal standing. Okay. Our one and only clicker question. So, oh, great. Thank you. So make sure you answer this one. The Earth's crust is thicker beneath the mountain because. Okay, that's interesting. No, I think it's 3. The numbers disappeared for me. It was something like that. The numbers could have changed. It didn't keep them for me because that's the way the software has been working this semester. The first 2 people to answer were correct. Only one person after them was correct. So discuss amongst yourselves what the answer here will be. It's one of the 2 answers that has 3. Oh, here. Okay, the correct numbers were this. I was able to go back and see it. Okay, let's see if it says polling is open, but that shouldn't be. Okay, try again.
Yeah.
All right. This time, we had one person change their vote. So let's go to Ashton. What's your reasoning here?
This made more sense to me. That one made the most sense to me.
Okay. Let me go to one of the people I know answered it correctly. Because like I said, the first two people, I don't know what you answer except for I see how many answers are on each one. The first two people answered the same. Rachel, I know you answered correctly. Also, she was the last one to answer the second time. So you answered this one. Why?
Well, I didn't know what the roots, what you were referring to in the roots, as far as, okay. But it just made sense because obviously there's gonna be more weight if it's above, so you have to balance between gravity going down and then
Right. The whole principle of isostasy is that you have to have a balance between the downward force and the upward force. And because those are less dense, the continental material is less dense, it floats higher. But to get the same downward force, you're going to have the total weight of the thickness of continental crust the same as the total weight of the thickness of oceanic crust. Ocean is more dense, so it doesn't have as much height to get that total weight. Continental is less dense, so it has to have more height to get to the same weight. But it comes down to you have to have the equilibrium, the isostasis, between the upward buoyant force and the downward gravitational force. Okay, continental drift. We've talked about continental drift a little. Let's just look at a picture here. Here's a picture of taking the continents and just trying to fit them all together. And they fit reasonably well. You see there's a really nice fit here between South America and Africa. Not quite as good, but pretty good here between North America, Europe, and Africa. And so looking at this, plus looking at fossil species, Wegener, that's how I pronounce his name at least. Is what, Alfred Wegener or something like that? Yeah, Alfred Wegener said, I believe that the plates of the Earth, the surface of the Earth is slowly drifting. And then scientists have done a lot of studies since then. Initially noticed that people said, no. They dismissed Wegener's ideas. They said, that doesn't make any sense. What would make them move? You know, it's like saying my house is going to move somewhere. Well, if you live the right place in California, you would say most definitely yes. You can find pictures of people whose sidewalks have gone like this, so it's no longer even connected because there is a fault that cuts across their property, cutting across their sidewalk, making one part of the sidewalk slide sideways compared to the other. Clearly, we can see and we understand now these effects. And if you fly over California, you can see faults. You can see places where things are on a grand scale sliding past each other. So now we know, yes, Wegener definitely was onto something. And it's the sea floor that leads to us really understanding this. Looking at the sea floor, we can see how material has moved over time. And so here's what's going on when you look at the oceans. We talked about the mid-ocean rifts. Here it says a mid-ocean ridge. The ridge is right over where the rift is because you have material that's coming up at that rift. And the material coming up is pushing the ocean floor away. So you can see in the picture, the ocean floor is moving away from that mid-ocean ridge. And then when it gets to a continental mass, it slides under or subducts. And you see the little orange thingies here? Those orange thingies are melted rock. It's melted, and so it's hotter, it's expanded, and it's floating up through the ground until it makes your volcano. So volcanoes are formed because of the grinding in the subduction here. You also are going to have some plumes and stuff occurring here in the middle where stuff is coming out. Here's another continental boundary with another volcano. So on your lab, you said, where else could you have island volcanoes form? Here we had subduction under, and this here, it's shown it more like another oceanic plate, but not the same one, and it's sliding under, making it. So that's what we see for the driving force for plate tectonics. It is this convection cycles. We call this, it says the word convection. Let me just put a box around it. Convection cycles, hot material flowing up at the mid-ocean rift, going to the sides, and then coming back down, that is driving the motion of our plates. So after studying the ocean floors, after seeing the magnetic fields in the ocean floor switching over time, scientists have come to accept that, yes, this is definitely what's going on. So here's a picture showing the magnetic orientation in the ocean floor. And it's showing at time 0, you have a normal polarity, that is, the magnetic field is pointing the same direction as it is today. Surprise thing. We didn't talk about magnets. The magnets have a north and a south pole. The north pole is technically the north-seeking pole. It's the pole of the magnet that points to the North Pole. Well, we've come to understand that magnets, just like electricity, opposites attract. So the north-seeking pole is the one seeking the Earth's North Pole, but it's seeking an opposite pole. So it's seeking a south magnetic pole. So here's one of the crazy things. Earth's North Pole is a south magnetic pole. It's a south because opposites attract, and the North Pole means north seeking. It seeks the North Pole. And so the green here is saying it's the magnetic fields frozen into the rock are aligned so that the north is pointing to the Earth's North Pole. Sometime later, the Earth's magnetic poles flip. And so the Earth's magnetic poles flip, and so the region here in brown, it's just the opposite. The material frozen into the ocean floor has its north pole pointing to the south instead of to the north. But then it's flipped back, so we have this blue, it's again pointing north. And over time, what you develop is a pattern where you can see the thickness of this, the thickness of this, my finger was screwed up here. The thickness of that. Those thicknesses are all reflected. I shouldn't have done the edge one because that's not going to the end. They're reflected over here with the same thicknesses and the same orientations. That indicates that, yeah, these must have formed at the same time together, but now they're spread apart. So that's how scientists believe they have evidence of the ocean floor's actual spreading over time because of the mirror reflection. And then going through and using dating methods, they can determine how long it's been since each one of these magnetic field reversals. And how long has it been? It's been close to 1 million years. It's something like 900,000, or I don't remember the exact number. Average time between pole reversals is around 200,000 years. What does that mean? If the average time from birth to death was 100 years, and you have somebody whose age is about 500 years, what does that suggest? You can't tell me you wouldn't be surprised to see somebody that's 500 years old. Why are you surprised they're 500 years old? Because they should have died already, right? The Earth is long overdue. It should have flipped already. So if you meet somebody that's 500 years, what's the first thing that goes through your mind? Are they going to die now? Are they going to die now? Is it going to be now? Right? You expect it to happen really soon. And so with the Earth's magnetic fields, we expect that it will be flipping sometime, quote, soon. Now that doesn't mean this week, this year, or even in your lifetime. But scientists are very carefully observing the Earth's magnetic field, and they're noticing right now some anomalies, which suggests to them that maybe the time is soon. And once again, soon might be maybe 20 to 50 years, we'll actually go through a reversal. Or maybe it'll be 200 years. We don't have a strong enough understanding of this to make those kinds of predictions. Although you can watch movies that will make bold predictions about this. Things like The Core. Let's just move on. Here's pictures of the Earth's tectonic plates. There are 8 major plates. So if you look here, you can see the major plates: the Pacific Plate, the North American Plate, the Eurasian Plate.
Where's the Eurasian?
Eurasian, Europe and Asia, Eurasian. Right, Eurasian is, you see it there as well. Let me circle one place. So that's the 4 biggest ones. The African Plate, there's a 5th one. I don't want to start naming the minor plates because you see things like, the Scotia Plate, that's definitely a minor plate. The plate of Juan de Fuca, that's a really minor plate. The Caribbean Plate, Nazca. I think Nazca is considered a major one. Oh, the Antarctic. Let's see how many I've done. 1, 2, 3. I've circled 7 so far. I think Australia is going to be the 8th. I think that's going to be our major plates, and then the rest ones are more minor plates. But these are the things that are floating around on the surface. And so places where you can have lots of earthquakes are going to be places where you have boundaries of these. Now notice the arrows. This here means that the 2 plates are moving apart. It's a diverging boundary. Diverging boundaries are going to be where you have your rift zones. So if you look mid-ocean, you're going to have often diverging boundaries. Here you have the Pacific Plate and the Nazca Plate is diverging. Also the Nazca Plate and that little Cocos Plate are diverging. And the Pacific Plate and the Antarctic are diverging. And the Pacific Plate and, well, that's converging. So you can look and see the directions the plates are moving with respect to each other. So I've circled a bunch of diverging ones. Then we have converging plates. So here, the Aleutian Islands are places where we have converging plates, can have subduction underneath and grinding, hence volcanoes. Converging there, volcanoes. Converging, volcanoes. Converging, volcanoes. Converging. The red places there are going to have volcanoes because of the converging. The places that were diverging, there's diverging again. The diverging are the mid-ocean rifts. Now, I talked about California and the motion there. This here is called strike, change the color, strike slip. Motion is parallel to the boundary instead of converging or diverging. And so that's a different kind of motion. So it's very interesting to track this, and you're going to see, okay, now I'm going to try to erase everything in one fell swoop. Think I can? Sure I can. Where you have earthquakes is always going to be somewhere close to those boundaries. So you have the most earthquakes of anywhere right there. Like Chile is earthquake capital. Those people are used to the world moving, and they have built very safe structures for motion. Everybody knows that we have a lot of motion here in California. And so the construction of the buildings is built to withstand the shaking. Now, it's kind of interesting. That does not mean that you make something really hard. When I was in college, one of my friends, we'll call him Paul Kumalen because that was his name. He was from the East Coast. He wasn't used to earthquakes. And we had a whole rash of earthquakes. And the first one that came on, he was living on the 7th floor of Sierra Towers. And so when you're on the 7th floor of a building, an earthquake happens. What do you suppose occurs in your room? You go, it's very amplified because the whole building is swaying. It's kind of like, the trees are gently swaying. My voice is kind of coming back. Well, my friends that were in their dorm room were noticing that the window was moving in and out. And they thought that was kind of interesting. But Paul was in the shower. And Paul wasn't used to earthquakes. And he thought the building's going to fall down. And so Paul runs out and runs down 7 flights of stairs and runs out of the building. And about the time he gets outside, he realizes, A, it's not shaking anymore. B, he wasn't wearing his stitched clothes because he was scared. Now, those of us who are used to earthquakes took lackadaisical things like I was sitting in the cafeteria during that earthquake, and everybody's diving under the tables because that's what they teach you from grade school up. And I was like, what? The building's not going to collapse. And yeah, that was silly of me. I probably should have done proper precaution. What I thought was the funniest, on a graduation day, the Lakers were playing the NBA Finals. We're sitting watching the Laker game. There's an earthquake. It was just kind of like a big jerk. And we're all sitting there, and about 30 seconds later, one of my friends says, earthquake, I guess. That's how significant earthquakes were to us. Okay, what causes the earthquakes? It's the sliding of the plates. The sliding of the plates creates stresses along little fractures in the earth. Those little fractures in the earth we call faults. And when the stress on a fault gets big enough, it'll slide. All right. Other pictures. We've talked about all of these boundaries. Talked about what's going on there. Well, we didn't talk about the trench. When we have this sliding under, it's called subduction. You're going to have a trench formed where one thing is sliding under the other because it's going to roll stuff under there. And so you have oceanic trenches are indicators of a subduction zone. And of course, you can see here the volcanoes that are formed out there in the ocean because of the grinding that's occurred. And notice this is associated with the continental boundary. It's the lithosphere coming out from the continental boundary where you have these volcanoes. So that, once again, was the answer on the lab for where else you could make island volcanoes. How the Himalayas, as I am told is pronounced there, the Alps, the Appalachians, and even the Rocky Mountains are formed. Did you know that mountains are actively growing? And they don't grow by eating oatmeal for breakfast. They grow because of this kind of action. If you have continental crust, pushing on continental crust, it will cause crumple zones. And that's what the mountains are. The mountains are the crumple zones of converging plates. And so the Rocky Mountains are believed to be caused by the Pacific plate pushing on the North American plate, the North American plate pushing and crumpling, having its crumple zone out in Colorado. And so the mountains grow, the Himalayas are still growing because of this kind of action. So mountains are not static. Okay, a transform fault is a place where the ridge has shifted. So that's what a transform fault is. Here, I've already talked about this. The San Andreas Fault. Anyone want to know where Monterey Bay Academy is? Start with, it's on San Andreas Road. Why is it named San Andreas Road? Well, because Monterey Bay Academy is right there. Well, okay. I better use a thinner pen. Monterey Bay Academy is right there. Very close to the San Andreas Fault. Monterey Bay Academy is not only beachfront property, it's on the beach side of that fault, I believe. It actually, the fault, goes right through there. So I think it's on the beach side. And you see Los Angeles? Los Angeles is already, quote, in the ocean. It's on the ocean side of the fault, and that fault is believed to be the boundary between the Pacific Plate and the North American Plate. Now, as I said, there's some conjecture that that boundary may have moved to something like this, that most of California might be in the ocean now. It'd take a lot more research for anybody to be conclusive on that. Okay, let's have ourselves a great Monday, and I'll see you again on Wednesday.